Welcome, everybody. The next speaker is going to be Folkert de Vries, right?
De Vries.
De Vries. Okay. So it's so hard for me. Holy shit.
I know.
I'm really looking forward to your talk. Actually, it's a talk about a web server that never allocates, which you would assume would be a Zig talk, but like from a Zig speaker. But actually, you come from the Rock community.
Yes. And also, I don't know if I should say it, but I use Rust, actually.
Oh, no.
So, you know.
Yeah, watch out for what people are going to say in chat.
Yeah, well.
Awesome. So could you introduce yourself a little bit, please?
Yeah, so I'm Folkert. I've been working on Rock for 4.5 years now, which is way too long, really. And also I work on various Rust projects. I with colleagues, wrote an implementation of the network time protocol called NTPDRS, and I'm now working on an implementation of zlib. So I do lots of low-level performance-sensitive things.
Awesome. So please give it up for Folkert, and let's get started.
All right. Yeah, so welcome to Nia, the web server that never allocates. So what is Nia? Well, Nia is first and foremost a proof of concept, and a lot of things here make a lot more sense if you keep that in mind. It is partially funded by AnelNet, which is a really cool organization that distributes EU money. If you do anything that you can somehow relate to the internet, they can give you money for that, if you're in the EU anyway. So that might be interesting for some of you. And also Nia is written in Rust. And so we don't need a lot of, Rust knowledge here, but it's going to come up a couple of times. So, don't be scared. So what is Nia really? Well, Nia comes out of sort of our wish to experiment with Rock platforms. And these Rock platforms have come up a couple of times already. But really in Rock, we have Rock the language, in which we can write a Rock application. But these always build on a platform. And these platforms are typically written in a more low-level language. And so we wanted to experiment mostly with sort of making Rock a language that is good at very specific domains, very many specific domains. So we can have very targeted platforms that sort of bake in certain assumptions about the domain. And in that way, these platforms sort of function like a domain-specific runtime, right? So many languages have just one runtime, and that runtime has to sort of always work for all cases. But we can have very specific runtimes for, say, game dev or GUI development or CLI applications, where just the functionality that is required within that domain is exposed to the Rock application. And so we can have a much nicer API and a sort of clean API boundary. So while we have many platforms in many different domains, we can also have several platforms in the same domain. And that is really what Nia is about. And these platforms can sort of make different trade-offs. They can make different assumptions. That's sort of the whole idea of these platforms. And so in particular, the platform is responsible for allocating memory. So when Rock says, hey, I want a string, hey, I want a vec, then it's up to the platform to determine what that means, whether it's going to just call malloc, which is sort of the default, or whether it's going to do something cleverer than that. So Nia is also a web server, and it really comes out of Richard's, who is maybe here somewhere, like frustrations with web development. So I don't really, work with the web all that much. The more I learn about it, the happier I get that I don't really have to touch that most of the time. But, it's based on sort of like struggles in production deploying these web services. And finally, and that's why I'm sort of really here, is that we can sort of solve the problems that we run into using low-level systems programming. And this has sort of been this cool journey that I've been on. And really my background is more sort of Haskell functional programming. And then over the course of developing Rock, I've become more and more sort of fell in love with this sort of, reading assembly and being really performance obsessed and learning all of these low-level tricks. So what we're looking at today is sort of, first of all, why did we design Nia? And then like what low-level tricks can we use to sort of fix these problems? So what are these web server woes? What are the problems that you face when you deploy a web server in the modern world? Well, really a web server should be simple, right? It's accept a request. We run some sort of code on that request. We get a response. We send that out. Go to one, right? The only special thing about Nia here is that this run the request handler thing part is raw code. But from your perspective, right, This rock function is just CFFI. You don't need to know anything about rock. We're just calling a foreign function. It's going to take a request. It's going to return a response. But this picture becomes much more complicated when you really sort of deploy it into the real world. And in particular, locally, resources are infinite, right? You have so much RAM, you could never possibly fill it with any workload that you could sort of dream up locally for a web server, really. Anything sort of organic anyway. But in the cloud, you pay for resources. Your resources are now finite. You're in this world again where actually you're very resource constrained, and you need to think really carefully about how you're going to use these resources, because you might run out. And running out of memory in particular is bad for your users. When your server runs out of memory, it gets killed, right? Jeff Bezos will sort of axe it, and that is not a good time, and not for your server, but also not for your users, because they will notice. They will notice that, they have to retry or whatever. My bank app actually does this from time to time, so, some Java programmer isn't truly doing their job right, but at least they haven't lost any money, so that's good. But really, have you tried turning it off and on again? It's just not great UX, and your users will notice this, and they will, over time, leave, right? It just doesn't give a good impression. And it also might really slow them down, especially if they're in the middle of some complex transaction. If you lose all of their progress, then maybe your system is still in a consistent state, but your user is now very annoyed. So we don't want that. Now, if you are, a sort of standard web developer, you are using Ruby or you are using Python or PHP or whatever else, and say that you actually have good intentions and you want to fix your memory consumption problems, what can you do? Well, the answer is not that much, because you are at the mercy of your runtime. This runtime determines sort of everything, right? And it's this layer that you can't break through. And these runtimes are mediocre at everything, right? They have to be not terrible at everything that you can throw at them, but that means they're not actually very good at your specific application. And so this is exactly sort of the problem that we face. In theory, right, there might be some sort of combination of settings for this runtime that is perfect for our application. These runtimes all have 100 knobs that you can sort of slightly manipulate, and maybe that gives you a perfect configuration. But it's really hard to find optimal settings because there are so many, they all interact. And then also, even when you do, your application changes or your access patterns change, and so the perfect settings are never perfect for very long. And even if you sort of find the perfect settings, what that means is really still sort of a heuristic. It's sort of a soft promise, but not a hard guarantee. And so you can't really engineer based on a system like this, because, it's just like sort of quicksand. You sink away. So we have two goals with Nia. Goal number one is to get a firm upper bound on the amount of memory that our server is going to use. And really, you always have a firm upper bound because that is what you pay for, but we want our server to work well within its bounds. So it should never overstep, it should never cross the line, and it should sort of operate within its limits. Goal number two is that a particularly memory-hungry request should not influence any of the other requests that are currently in progress. Because normally what happens when that process gets shut down, there is one sort of bad actor in there, one bad request that sort of made memory usage really spike. Or, there is some bug, and so there are some requests that are bad, but many of them are really quite innocent, and they also get canceled when the whole server goes down. We want to prevent that. So, sort of good citizens should continue to run uninterrupted. So, in practice, this problem is actually quite hard, the second problem of figuring out which request is actually good or bad. And existing runtimes really can't do this, because they throw all of the traffic sort of on one big pile, literally actually on one big heap. And the problem of sort of disentangling that is surprisingly similar to fallible allocation, which is something that I suspect you are all more familiar with at least. So this is some Rust code. These are two functions from the standard library. They are defined on sort of a growable collection type. And so the first method, reserves some additional memory. And the thing is that this function can fail. So when you run out of memory, when your allocator is full, this will actually abort your program. Now, I was talking to some people that work on getting Rust into the Windows kernel, and also later people that work on getting Linux or Rust into the Linux kernel. And for them, that is a major problem, because your user app first of all, resources are infinite on your local device, and so it doesn't really matter. And then also, if a program sort of crashes, that is still sort of fine. But your kernel should not crash. Your kernel should not abort if some memory allocation fails. And operating systems really need to handle this case properly. So they started playing around with sort of additional APIs that usually start with this try prefix, where you always get a return value indicating success or failure, and this function will never sort of blow up your program. And so this seems really nice because now we can at least catch when allocation failed, right? We get some value back and we can branch on that. We can sort of switch on the two cases. And we can try to recover. So let me illustrate this with the help of my friend the camel. Camel the allocator, camallocator. And normally when we sort of load, allocations onto our camallocator, then everything is fine. Everything is good. It's in its lane, flourishing. And over time, right, these allocations sort of get removed. Now, in the case of sort of an out-of-memory event, really what's happening is that our camallocator is already actually quite strained. It's already under sort of heavy load. And now when we add one more allocation, we add the malloc that broke the camel's back. The thing is, this final straw isn't actually the problem. This final straw was a perfectly normal allocation. Everything about it was good. It was just ill-timed. It was unlucky. And the thing is that if we now catch this with one of these fallible allocation APIs, there's not really all that much we can do because the current request isn't sort of at fault, or the current allocation isn't at fault for that we're now out of memory. The problem likely sort of occurred way earlier where, due to some bug, we didn't clean up memory where we should have, or we allocated much more than we should have. But we can't really track that down from the current location where the problem actually shows up. So these are sort of temporally separated, which means that tracking this bug down is really tricky in practice. And I show this with our camallocator because in practice we get sort of much more boring graphs like this, where we can see that we have some server and it has high memory usage, so it spikes, and then it gets killed, and then you sort of reboot it and it spikes again, and then it gets killed. And then eventually the people that posted this image, they actually make their server just use less memory and restart automatically instead of having it be killed. So over on the right of that image, you can see that it stays below the red line. So they did that artificially, but still the server sort of keeps on rebooting as it runs out of memory. That is not good. So what can we do? What are our solutions here? And these are really sort of Nia's design. So these are not like universal good answers, but these are the answers that we came up with. So first of all, our starting point is actually pretty good. So Rock is a much faster language than the sort of status quo in the web space, right? Winning from Ruby is very easy when it comes to speed. So Rock is relatively fast because we're compiled and we can use LLVM for all the optimizations, etc. And also we use reference counting as our garbage collection sort of approach. So we have no sort of like stop the world garbage collector, but something actually very similar to how Rust and C++ sort of deallocate when values go out of scope. So already for a language for a web server, we're actually sort of looking pretty good. We can do better though. So problem one was get a firm upper bound on the amount of memory used by our web server. And the way that we fix that is by making one request for memory. We could argue whether this is an allocation or not. I'm going to argue that because we don't call malloc and we don't call free, I will claim that we make 0 allocations. But, sort of shaky. In practice, we make one very large allocation using mmap or something similar. So these are operating system primitives that gives you large sections of memory sort of in one go. Now, so perhaps we make one allocation, right? Instead of never allocating, we allocate once. But that's all we'll ever do. We'll never give that memory back, and we'll also never ask for more. There's literally no code in the program that would ask for more than that. In theory, right, we could pre-compile. We could sort of hard code how much memory we're going to need, and we could sort of do that with a constant. I believe that is what Tiger Beetle at least used to do. It might still do that. The one limitation you get there is if you want to change that number, you need to recompile. And that might work for them, but it doesn't really work for us because we want Rock programmers to only have to know Rock and not install like a whole, tool chain for compiling native code. So we don't want them to have to recompile. So we need to be a little bit sort of dynamic. But in practice, what we do is we sort of start the app, read some config, do some math, outrolls a number of bytes that we allocate, and that is sort of all the work we ever do allocation-wise. Sort of an interesting observation here is that now our memory consumption is sort of always maximal. We're going to use all that memory, right? When you mmap, it's actually not really allocated. It's just sort of there in the administration, but only when you really touch that page does it really sort of become yours. But we're going to touch all of these pages eventually, and so we're going to actually always be sort of high memory usage. But that's fine because we paid for that memory, right? So we may as well actually use it. Solution 2 is harder, is trickier, requires a couple more steps. So our problem was a memory hunger request should not impact any other request. And the way that we're going to fix this is by giving each request its own little allocator, its own little region of memory that it can allocate into, and no one else can. And this is a fixed amount of memory that it gets. And in practice, these sort of work like bump arenas. So allocation into these is very cheap. And also, we don't really free memory there. Only at the end, when the request is over and the response has been sent, do we clear the whole thing in one go. And that is just resetting a pointer to an earlier address. So that is very fast too. So already, we should be faster than most web servers because they need to do malloc, and we don't. Now, in practice, we call these little slots buckets. And what's interesting here is that we now run into a hard limit on the number of concurrent requests that we can serve because we only have so many of these sections, right? We have this one big allocation. We chop it up into these buckets. And then there's only so many of them. We only have finite memory. And every request needs one of these buckets in order to actually do its work. So, this is actually quite limiting. But we get a magic power, which is that we can do math. We can actually do math, right? We know how many buckets we have. And so based on that, and based on how much memory an individual request needs, we can calculate how much total memory we need, or sort of vice versa. If we know the total amount of memory we have, and we know how much an individual request sort of requires for processing, then we can know sort of how many buckets we can have, and so how many concurrent requests we can actually serve with a particular instance. This does also sort of follow into the fact that it's now very unfortunate if you have huge outliers, if you have particular requests or particular like arguments that you can give that use a lot more memory than the vast majority of your requests, because the buckets need to be sort of big enough to accommodate them, and that means for most, you waste a lot of space. So in practice, it might be sort of advisable to split that up into different size classes and run multiple instances and have some routing logic so that you can use your memory most optimally. This has all been the happy case though, right? If memory sort of isn't a problem, if our bucket is big enough, then everything is nice. The really tricky part is, what if it isn't though? What if we get a request that actually goes over its limit? It goes out of its bounds. Now in this case, we need to recover. But first of all, we can actually log this particular request because this request violated sort of our assumptions. It's not just the random sort of memory allocation that was ill-timed. No, this is actually a problematic request. And so we can sort of, we really want to know about it, right? It is actually helpful to know what went wrong, and we can actually track it down, reproduce it, etc. The next thing we're going to do is send a proper error 500 when this happens. So normally, when you have that web server that gets canceled, the sort of connection gets interrupted. But we can properly send a internal server error back in the case of an error. And finally, when allocation fails very deep down the stack. Somewhere in an allocation function, we run out of memory. We're now in that allocation function. We need to somehow get back up the stack to a place where we can accept a future request. How do we do that? Well, we do that using setjump and longjump. Who here has ever played around with setjump and longjump? See, cool. Okay, so that's roughly half of people. And of course, this audience is extremely biased, right? But it's like in practice, few people know about this. And when I first heard about it, I was like, no, like that can't work. Surely not. Like that would be so cursed. Please, no. In practice, this is an example using setjump longjump. And what setJump does is really it takes a snapshot of the current state of the program. So a snapshot of current registers, also the stack pointer and the instruction pointer. These are really the crucial ones. And then we can sort of continue the program and later sort of restore this snapshot with a long jump, which sort of takes us back to the place where the setJump was called, where the snapshot was made. And so some details here are that setJump, when it makes a snapshot, it returns 0. So this program would print 0 and then not take the branch. Then we have to imagine that there's actually a lot of logic in between. In particular, there can be function calls in between. Right? So this long jump can be in a very nested stack frame, and that is why it's called a long jump. It cannot just jump within a function, but it can jump between functions. It can cross sort of stack frames. And now when long jump is called, we sort of jump back to line 7 in this case. So it sort of looks like setJump actually returns twice, but this time it will return the value that is given to long jump. So it will return 2, and now we take the branch. So we can sort of recognize that the error happened, right? Or that the jump happened. Now, because this is a piece of C code from the internet that is longer than 10 lines, there's undefined behavior in it. That's what you get. In practice, you aren't allowed to use the return value of setJump in this way. You aren't allowed to bind it to a variable. You're only allowed to branch on it or to sort of make control flow depend on it, not data flow. So what makes this worse is that it's from like a university website. So I don't know. So because this is, a systems programming conference, I thought I'd put in some assembly because this is the only place where I can get away with that. So I thought this was really cool because setJump and longjump, even after reading the docs, like the C docs, were really magic to me. Like, how could that ever work? How could that ever be something sensible? And the fun thing when you sort of gain your confidence in this sort of world is that you can actually go to source. You can, well, actually, this is trickier than it seems at first because, of course, libc is linked dynamically normally. But I made a little Zig program. And I set it to use muscle, and then you can object dump it, and you can actually look at the source of setJump. And we can see here that we have all of these register names, and these got stored into what is that jump buffer thing, that env, into a big array at a particular offset. And then we can also note that longjump does the exact opposite. It takes this big array and moves the values back into the registers, and ultimately it jumps to a location that is also stored in this big buffer. And so, like there's some like arithmetic in here, etc., but you can go sit down and actually understand this. And I thought this was sort of quite nice that I now actually understand how that works. And it's sort of less cursed now, even though it's still sort of slightly cursed. Especially, we'll get back to that. First, like this is now actually how the program sort of looks. So we have this loop. It gets some work item out of a queue. We're doing asynchronous things, so we need to await that. Then we take a snapshot of the current state, so we can get back into this loop when allocation fails down the line. But assuming it doesn't fail, setJump will return 0, and we can actually call rock logic on this piece of work. And if that doesn't fail, then we sort of go back to the top of the loop, and we continue serving requests. Now, if something does fail, it'll fail in this function called rockAlloc. This is what rock calls when it wants to perform an allocation. And so this let pointer ... here is going to look at that big array of buckets, and it's going to pick the right one for the current request, and it's going to try to allocate. If it doesn't fit, that will return a null pointer, and we can catch that here. And in that case, we jump back up the stack. Right? So we're very far down, and we can now jump all the way back up into our loop. But this time, that sort of setJump call is going to do a second sort of fake return and return 1, which means that we end up in the other branch and we can handle that failure. So we can sort of do the logging, do any cleanup that we need to do, send back an error 500 response, etc., and then just continue with the next request. There are some caveats to this, though. So setJump longjump is still cursed. Both because we can skip skip destructors, so that is sometimes bad because you might forget to unlock a mutex. But also this returning twice behavior, which is sort of in effect what setJump does when it gets jumped to with the longjump, is not something functions are really allowed to do. So in LLVM, there is a special annotation that you can add to a function, But Rust doesn't have this annotation. And so this function is in effect so unsafe that even an unsafe block cannot contain it. And it is also not exposed in the Rust libc library. You have to sort of externifn it yourself if you really want to use it. In practice, I actually use the inline asm sort of variants of these functions just so I know exactly what they're going to do and they aren't going to do any sort of funny business. All right. A second topic, or sort of something that is really quite tangential but makes the whole solution a lot more complicated, is that we also want to do async IO in this server, because async IO sort of makes sense for web servers, right? Like, we don't want a whole thread to hang when a particular request handler makes a request to something in the outside world. So in practice, the thing is, though, that I don't understand how async works, and Rust doesn't understand how async works either. Rust only knows how to do a syntax transformation on code like this. It doesn't really know how to run it. So when we have an async function, and it does some await, all that Rust knows, the Rust compiler knows, is how to turn this into a state machine that we can pull. So we can sort of continually ask it, are you done yet? Are you done yet? Are you done yet? Are you done yet? And either it'll sort of say, nope, still blocked, still sort of waiting for something to complete. Or it'll say, yes, actually, I am done. Here is a value that I've produced at the end of my computation. Now, this is cool, but it still doesn't run, because we need some program that will sort of call these pull functions in an efficient way. We can't just, we could, but we don't really want to run them in a loop, right? In a hot loop, and sort of continually pull them. That would be inefficient and unfortunate. So instead, what Rust allows is for sort of user code, for user packages, to write a program that is going to do this polling. These programs, or these sort of packages, are called async runtimes, and they determine exactly sort of what async is going to actually do in practice. And so we have several sort of off-the-shelf options here. We have one called Tokyo, which is for desktop applications. We actually use that in the Network Time Protocol client. And we also have Embassy, which works on embedded hardware. And it turns out that sort of async await is a surprisingly cool idea on embedded, where we can sort of wait for a particular thing to fire or a particular timer to run out. So instead of having to sort of manually set that up every time, we can just have the async machinery take care of that for us. Unfortunately, we can use neither of these two solutions, because the embedded one doesn't really work across multiple threads. It doesn't make good use of many threads. And the Tokyo one will allocate, and we can't have that, right? We need to control allocations. We don't have custom allocators in Rust. Sadness. And so we need to actually build one ourselves. I'm not going to really go into the technical details of that, but we wrote a whole blog post about it. And the blog post isn't important. What's important is the code sample that goes with it, which is, to my knowledge, the first and only sort of practical example of an async runtime in Rust that is simple enough to understand, but also complicated enough to not be trivial. So we really actually get into the details of how really does the operating system know when sort of a blocked call is ready for doing more reading or writing, and how does the program notice this? This has always been magical to me. Like, if we have async, we always learn, like, okay, if something blocks, then the computer is going to do something else. So it's going to jump to some other piece of work. But how does it ever know that it should return to that other piece of work in an efficient way? Clearly, we don't want it to just like randomly go back there, because that would be sort of terrible for throughput, and it might be really wasteful. So how does it do that? And it turns out it cheats by adding an extra thread that is able to sort of re-enqueue jobs into the queue of work that we've seen before. So if you want to learn more about how Rust async works, then I really recommend this blog post that I wrote. All right, so some future work. We need to make this more robust. It is a prototype. I think I've removed all of the race conditions. I'm not sure I removed all of the race conditions. You never know. Also, we should run actual rock applications. So we have some basic ones working, but the interaction between platform and application is something that we're still sort of playing around with. And so we haven't really run serious applications with this architecture. And also next week, I'm going to be doing some benchmarks at the local university where they have a bunch of equipment for like measuring power draw. So that should be really fun too, because in theory, we should be faster than like any Rust solution that uses malloc, just because we don't allocate on the fly when handling a particular request. But it's been a little bit challenging to sort of find a benchmark that isn't really fake, but also shows this in a clear way. In practice, it turns out computers are pretty fast and sort of good at executing instructions. All right. So in summary, custom allocators are a superpower. I am so happy that Zig sort of put this back on the map, because I think this was sort of not talked about all that much, or at least I would have never found it coming from that Haskell background. But they are so a superpower. And I also feel like we still haven't sort of seen their true power yet. And it just requires sort of Zig being used in more places, or perhaps other languages adopting these features to sort of see the real power of sort of more specialized memory allocation. With hard bounds, we can do math. And math is actually really useful. We can do engineering instead of just guesswork. It's so nice. We can have actual sort of faith in that our systems are going to run reliably. And so I think designing systems in this way is sort of a really good thing to do. Rock platforms combine the convenient and the performance. So we can have very low-level code that sort of manipulates the stack and does whatever, and it can live alongside this Rock application, which really doesn't need to change even if we were to swap it out to, a platform that is less fancy. One that we actually have today is just a box standard. We just use malloc and we are a normal web server. We can have the same program run on both of these platforms and just sort of see like whether it works in practice and what the trade-offs are. And I guess in closing, keep building programs that never allocate. Thanks.
Thank you very much, Folkert. That was a very nice way of ending your talk.
Thanks.
So, do you have any questions from the audience? I think this is the kind of talk that really benefits from that.
Okay, so at the beginning, you show all the different buckets and you comment about how they're all the same size. Have you ever considered over-allocating past the size of the actual memory and using something like ZSwap to like compress all of the bytes that are like generally 0 because those requests never touch it?
I have a limit for how cursed this program should be, and this seems past that threshold.
Yeah, it's probably not a good idea, but it's an interesting one at least.
Yeah, sure.
Up there. Well, in the meantime, while August executes the search algorithm, what about stuff like fetching data from the database, right? Because you will have some type of requests where you will discover afterwards how much memory you're going to need. Do you have a strategy for that?
So I think in practice, the way that you would use this is to just sort of start off with sort of really overestimating how much memory your requests use in practice and gradually trying to sort of bring that number down over time. Because most people don't actually really think about like how much memory does an individual request take. That is something you can't really figure out. You can take an average, right? You have some amount of throughput and some amount of memory used. But really, how much of that is the Ruby runtime versus actual, doing useful work in your application? That's unclear and really not information you can find out with current architectures.
Yeah, I guess you could also partially solve it, at least in the database case, using like pagination. So I would totally love to see your talk next year, like an ORM that never allocates.
Yeah, I mean, so like as soon as you have these constraints, of course, you need to sort of think about maybe new patterns make more sense within these new constraints. And, we want to find out how we can make that work in a convenient way.
Nice. Okay, let's go.
Yes. So I would call this usage of set jump and long jump highly questionable in Rust. So I have multiple questions about that, but I will condense them.
I agree with you. So, I was speaking with one of the Rust core developers last week, though, and they said that we could make it less cursed, paradoxically, by adding more assembly.
But the main question is, why don't you actually just use a result? And the second question, I will just follow up right away, is how do you handle when you, for example, open a file, run out of memory, and then do a long jump? That file will be leaked, and yeah.
Yes. So in effect, we would need, we would need you to not do that, which we can actually do, right? So in practice, what happens is that the rock call, basically, we make sure that there are no Rust resources allocated between our set jump and our call to the raw code. That is just all like destructor free. So that means that at least on the Rust side, there aren't any resources that we leak. And then on the Rock side, we have to make sure as compiler authors that things are going to work out well. So we might in the end sort of need some sort of unwinding to guarantee that. So far, we've just been sort of leaking things, and it's fine. Because it's fine because we have that bump allocator, right? And we just sort of move that back to the start. So as long as you don't have any sort of non-memory resources, you're good. You're right that if you want to really open a file, then we would need to figure something else out. And there's some options there.
So,
right. So work in progress, right? Future work.
and so why not the result?
So result where?
Like how you use try in Zig, and I guess Rust is the same, like this result enum. Why doesn't the allocate function just return a result that says, I couldn't allocate, this is out of memory? Then you unwind the stack, run all your destructors, etc.
No, because that allocation function is in Rust, but it's called from raw code. So we would be unwinding over FFI boundaries, which is not really allowed, and something that like Rock doesn't super support. Also, it would be relatively slow compared to sort of doing the direct jump. So we're really sort of in a very constrained environment when we run out of memory and we're very deep down the stack. We don't actually have that many options, and we don't really want to unwind if we can help it, because that'll add a lot of complexity.
Okay, thanks.
So you want a language that gives you custom allocators that allows you to do unsafe stuff. And you want to be able to look if you have resource deallocation like destructors running in a piece of code, and you would like the language to allow you to do that auditing easily.
Correct.
Yes. That's it. Next question.
And I haven't really, focused on that, but we also wanted to do HTTP and potentially HTTPS. And when we started this project, that situation in Zig was just sort of not that mature. That and I am much more comfortable in Rust, so that was sort of easy. And in Zig, it would have required just a bit more work. I don't hate Zig. I'm here, right? It's like we use Zig a bunch. I really like it, actually, but we didn't pick it for this project.
Yeah, that makes sense. I'm actually thinking about your developer experience. That's my perspective.
Yeah.
In any case.
I mean, the hard things were race conditions. The rest was just fun, really.
So, well, thank you very much. Let's give it up for Folkert.